Hey guys, in this video we're going to take a look at reference angles and how these are very, very useful things when it comes to evaluating trig functions of any angle, because it means that we won't have to use our actual unit circle to do this. We can actually narrow it down by quite a bit. So let's go ahead and start by kind of talking about what a reference angle is. Its definition is the acute positive angle formed between the terminal side of an angle theta and the x-axis. And so one thing worth mentioning here is that it's formed between the angle theta and the x-axis, the terminal side of angle theta and the x-axis, but we also write it as theta prime. So really quickly, I just want to talk about notation here. If theta is our angle, okay, then this theta prime is just our reference angle. And again, it's our positive acute angle formed between the terminal side of an angle and the x-axis. So this is kind of a neat little applet that I've used before to kind of explain this, but if you were to imagine here, we have two angles. It looks like we have one in black, okay, so this 59-degree angle, and then we have this inner angle in blue here. I want you to know that this inner angle in blue is our reference angle. So that is to say that given this angle that's 59 degrees here, if we look at the terminal side of this angle, and we look at the x-axis, it's kind of like saying, what angle is this angle forming between the terminal side and the x-axis? 59 degrees. You'll notice, though, that as I cross into quadrant 2, let's maybe say I have a 135-degree angle. My angle may be 135 degrees, that's my theta, but looking at my terminal side, what's the positive acute angle that it's making with the x-axis? This terminal side is making a 45-degree angle with the x-axis. And you can see that as I rotate through the quadrants here, that blue angle representing our reference angle is always kind of telling us what angle our terminal side's making with the x-axis. So some things are worth mentioning here. One is that the biggest our reference angle ever gets is 90 degrees, because I couldn't make a bigger angle between my terminal side and the x-axis here than 90. Once I cross over into quadrant 2, my reference angle gets smaller than 90 again. And if I go back into quadrant 1, it also gets smaller than 90. And the same is true down here. You know, my reference angle could be 90 at most with the x-axis, but as I go either side, you can see that it gets under 90. And the smallest my reference angle can ever get is 0. That would be the smallest angle of rotation I can ever make between the terminal side and the x-axis, is that they coincide 0 degrees there. Lastly, I kind of do want to look at, well, what if I did, say, a negative angle here? Hey, the same thing is also true. If I have a negative angle, it just means I'm rotating clockwise, but the angle I form between the terminal side and the x-axis is this positive acute angle. And if I say I had a negative 130-degree rotation, well, then it would take me another 50 degrees to pick up and get over to this negative 180 here, or the x-axis. So as we look at reference angles, which is going to be kind of an important idea here, I want to kind of look at how reference angles, okay, are related to trig functions at a given angle. So what we're going to do is we're going to kind of explore something here. If I look at, say, the sine of 30 degrees, and I really mean using my unit circle here. If you look at my unit circle, our 30-degree angle is right here. So here's my terminal side. I'm going to go ahead and sketch this in. And here's my initial side. And here's our 30-degree angle. What I want you to notice is that with this 30-degree angle here, I get these, say, cosine and sine values respectively around the outside. What if we pick another angle that has the same reference angle, makes the same angle with the x-axis? And so there are several of these. Another one would be 150 degrees. That is to say that if I were to look at this as my angle, 150 degrees, and I really want you to see this here, this 150, it makes a 30-degree angle with the x-axis here. So I suppose the other two angles I can think of that make 30-degree angles with the x-axis would be 210. 210 here, if I were to sketch this in, 210, that would make a 30-degree angle with the x-axis right there as the reference angle. And if I were to say a 330-degree angle right here, it also makes a 30-degree angle with the x-axis, regardless of the fact that my initial angle is 330 degrees. So what is it that these all four have in common? The fact is, well, they all have a reference angle of 30 degrees. If we were to take the time now to drop in altitude from our point on the exterior of our unit circle back to the x-axis, what you're going to see is these four triangles appear. And this is really what I want you to notice. How do these four triangles that all have a 30-degree angle with the x-axis, how are they all related to one another? And I hope that you see that all four of these triangles are absolutely congruent. The only difference would be that instead of having maybe a positive root 3 over 2 and a positive 1/2 as my dimensions on my triangle, if I'm talking about my 150-degree angle here, which also has a 30-degree reference angle, I'm going to have the same two values as I do over at my 30-degree angle. It's just that my x values will be negative by the fact that we're just simply in the second quadrant. And looking at all of these ordered pairs that fall on the outside of this unit circle at any angle that makes a 30-degree reference angle, I hope you notice that they are all the same. So what we are going to do, as a matter of fact, is look at a very, very procedural way of just using reference angles to evaluate trig functions of any angle, as opposed to actual angles. So everybody's going to get this paper from me, but let's take a look at what it says. It says finding the value of a trig function of an angle theta in standard position, but by using its reference angle theta prime. So our reference angle theorem, this is a pretty neat thing here. It says the reference angle theorem states that to find the value of a trig function of any angle theta, the first thing we're going to do is determine the value of the associated reference angle theta prime. And then what we'll do is depending on the quadrant in which theta lies, we're going to assign either a plus or a minus in front of it. And that's that all students take calculus mnemonic that we use to kind of remember which trig functions are positive and in which quadrants here. So let's take a look. As a matter of fact, what if we were to kind of try a few of these here? As a matter of fact, let's throw out this one here. What about the sine of 240 degrees? So first things first, how might this work if we're going to evaluate trig functions using reference angles? I want everybody to focus on these 4 steps that you see here. So it says, first of all, what we're going to do is find the reference angle theta prime for the given angle theta. So once we do that, we're going to use our reference angle instead. But when we say 240, I usually just make an itty bitty sketch here, and it doesn't have to be pretty, but 240 degrees would lie somewhere in our third quadrant by the fact that it's between 180 and 270. So looking at this, here's our 240 degree angle, 240 degrees. Yuck. Let me try to fix that a little bit here. 240 degrees. The question is, but what is the angle that my terminal side is making with the x-axis here? And so a real quick calculation, we could take our entire 240 and subtract off our 180. It means that it's leaving behind a 60 degree angle. So this means that if our given angle theta is 240 degrees, okay, then theta prime, or its reference angle, is just 60 degrees. So after we find our reference angle theta prime for our given angle theta, it says rewrite the original trig function with the reference angle theta prime instead. So what does it mean? Well, it means that the sine of 240, what I'd love to see everybody do is we're just going to rewrite it as the sine of, and instead we're just going to use the reference angle. The reason why is because we know that any angles that have the same reference angles are going to produce the same values on the outside of this triangle or this circle anyways. So using the reference angle 60 degrees is a little bit more convenient than having to think about, what were my values over here at 240 degrees right there. It's a little bit easier to remember our values at 60 degrees, okay? So step 1 was to find our reference angle. Step 2 is to rewrite the original trig function using the reference angle theta prime. Step 3 is going to be put in place or affix the appropriate sign to the trig function, so positive or negative, depending upon which quadrant the angle terminates in. So remembering our mnemonic, all students take calculus, recall that this just kind of helps us remember that the only thing that's positive in the second quadrant is our sine values. The only thing that's positive in our third quadrant are tangent values. The only thing positive in the fourth quadrant are cosine values. And everybody, all of them, are positive in the first quadrant. So as I look at this and I say, okay, I am finding sine, but our 240 degree angle, which quadrant did it terminate in? It terminated down here in the third quadrant. And so since I know that tangent's the only thing that's positive down there, I'm going to affix a negative out in front of here because I know sine has to be negative. And so last but not least, what we're going to do is evaluate the trig function. So what do I know about my sine value at 60? Well, I can use my unit circle to help me out here, but the idea is going to be that I don't want to use my unit circle in its entirety because this thing is very, very hard to memorize. So check this out, your unit circle right here. We're going to get rid of it. And what I'd love to do is actually get rid of all that. I would like everybody that's looking at this video here, we're going to redraw our unit circle on the back of your unit circle page. And so people laughed at me today, but this should be like a 2-minute or less exercise. And so what do we put on this unit circle that I'm going to sketch and not be that detailed? Well, remember that our unit circle has a radius of 1. So if this is the point 0, 0, then our 4 points on the quadrantal angles are all going to be 1 unit away from the origin in either a north, south, east, west, or direction. So we have 1 unit to the right is 1, 0. 1 unit to the left is negative 1, 0. How about 1 unit above would be 0, 1. 1 unit below the origin would be 0, negative 1. Beyond this, there are only 3 angles that we tend to put on here, and these tend to be our 30, 45, and 60, because since all reference angles are acute, it means that all of the reference angles we're going to use are going to be somewhere up here in the first quadrant. So we're going to fill out some ordered pairs here, and I tell people, you always fill out ordered pairs, but there's something that all 3 of these have in common, and that is that they're all over 2. Now, as far as patterns go, okay, you want to remember that it goes down from the top right there, 1, 2, 3, and then it goes back up from the bottom right to the top there, 1, 2, 3. And so I suppose what I mean to say is, starting up here on my top ordered pair at my 60, the x value is 1, like I've got written right here. And then we go down, we get root 2 and root 3. And we start down here, this is a 1 and a root 2 and a root 3. So when I look back over here and I say, well, you know, what's my sine of 60? Instead of having my unit circle present, which I'm not going to let you use, we can just sketch this on the back of the paper or on a piece of scratch paper. But we just go over here and we look at 60 degrees and we say, well, if I want my sine value, I really want my y value. So this is going to be root 3 over 2. But what do I know about this? I also know that it's a negative. So we say negative sine of 60, which would be a negative root 3 over 2. Believe it or not, if we were to go look at our unit circle now, which I totally deleted, let's see if we got it here. If I go to 240 degree angle, 240 down here, you're going to see that our sine value is negative root 3 over 2, which is exactly what we had gotten here just using a reference angle. So let's take a look at maybe a few more of these, and to make it a little bit more worth your time, we'll use some of the exercises that I'm going to ask you to do. But let's take a look at, say, maybe a cosine value here. So cosine of 150, could we use these steps here to take us through how we would do this more conveniently? Well, first of all, let's find our reference angle for 150 degrees. So you can make a little sketch somewhere, find a little spot. But 150 degrees, remember, would be between 90 and 180. As a matter of fact, it would stop about right there, 150. What we're looking for is, but what's this little reference angle it makes with the x-axis over here? So I noticed that my theta prime is 30 degrees. So what we're going to do then is we are going to rewrite the original trig function with the reference angle instead. So instead of using the 150, we're just going to say, look, guys, this is the same as the cosine of 30 because they make the same triangle over here on our right, or on our unit circle. Step 3 is going to be, well, hey, you know, fix the appropriate sign depending upon what quadrant we terminate in. Well, good thing I made a sketch here. I'm in the second quadrant, and if I put in my mnemonic here, all students take calculus, I notice that I'm finding cosine in the second quadrant, and the only thing that's positive in the second quadrant is sine. So I better put a negative out in front here. And then last but not least, we say, well, what's our cosine of 30? We can just go over to our unit circle over here and say, well, our cosine at 30, this is our x value right here, so root 3 over 2. Our answer is going to be negative root 3 over 2. Okay, maybe just a couple of other ones here to take a look at how we might do this with reciprocal trig functions, or maybe a tangent function. So let's head over to our, say, or radian measurement rather. Let's take this tangent of negative 2 pi thirds, for instance, here. So, you know, in terms of our sketch, remember that when we're talking about a negative angle of rotation, we're rotating in a clockwise direction. So we'll start here on our positive x-axis. But also remember that pi is the same as 180 degrees. So when we talk about pi thirds, you can imagine that it takes 3 of these things to get all the way over to pi. Well, negative 2 pi thirds is going to lie right here, negative 2 pi thirds. So we only sketched this to find out, but what would my reference angle be? And we can see that in radians, I think this is a little bit easier to do. We say we had just like a leftover pi third here. So instead of doing tangent of negative 2 pi thirds, let's do the tangent of just a plain old positive pi thirds. And because we're terminating in the third quadrant and we're finding tangent, we know that we have to have a positive value. I will affix a positive out in front. So beyond this, how do I find my tangent of pi thirds? Well, remember, tangent is y over x. And so as we go up to pi thirds here, or our 60 degree measurement, we're going to take our root 3 over 2 divided by our half. Worth showing our work on just maybe one of these here. Root 3 over 2 divided by a half, and it's positive. So this would be the same thing as root 3 over 2 times 2 over 1. We see our 2's kicking out here. So we get root 3 times 1, so root 3. All over 1 times 1, 1, so we get root 3. This would be what we'd put in this spot right here, root 3. And so lastly, let's take a look at maybe a reciprocal function, also in radians. So number 28 is just a very good example here. So if I wanted to do the secant of 3 pi fourths, hey, again, let's make a little quick sketch of our angle, remembering that in standard position we lead from the positive x-axis, and that if this is pi, it would take me 4 pi fourths just to get over to here. We can imagine that we split this up into 4 equal sized rotations. So 3 pi fourths is really right here. The idea being that if this is 3 pi fourths, we want the reference angle. And so that would be our remaining pi fourth rotation right there. So instead of secant of 3 pi fourths, we're going to write secant of, well, no, it's secant of pi fourths because we'll get the same values anyways. And because we're finding our secant in the second quadrant, Remember that secant is the reciprocal of cosine. And so since sine is the only thing positive in the second quadrant, cosine must be negative, well, secant must be negative. So the last thing we're going to do here is just go evaluate, and this is where this picture comes in handy here. Going to our pi-4th measurement, our ordered pair here, remember that because secant is the reciprocal of cosine, our cosine value is root 2 over 2. That means that here we're going to get this negative that we'll carry through, and we'll get 2 over root 2, which after we rationalize this, which is very important here, we would get negative 2 root 2 over 2. And we can also see that sometimes we get factors to cancel. And so we get negative root 2 over 1, or just negative root 2 would be this value right here. This beats the heck out of having to use the entire unit circle, which nobody's going to draw on their paper in under 2 minutes. And our unit circle tends to not have negative angles listed on it. So it's a lot easier to just associate these with positive acute angles or our reference angles, okay? So in terms of finding values of your trig functions at any given angle here, I want you guys to be using these 4 steps here. Find the reference angle instead, rewrite it using the reference angle, put a plus or minus depending upon what quadrant you terminate in, and then use this quick sketch that we always are going to make on our paper here in order to get us through this. Cheers.